Thank you all for coming. This is, we're going to be giving an introduction, well, I'm going to be giving an introduction to quantum computing, but I'm going to take a little bit different of approach than most people do, because what they do is they come at it from a very physics/mathematical background, and that's very important to understand, but we've come a long way in terms of some practical ways, so hopefully it makes it a little bit easier. Let's see if that works. So, just a little bit of an agenda here. We're going to kind of go back and forth between some concepts, but essentially explain in a nutshell what is quantum computing, some of the basics. There's different types of quantum computers. There's quantum simulators that are, and what I mean by quantum simulators is specifically software simulators, and that'll become apparent why I call that out in a minute. Well, a little bit later, I should say. Some practical applications today that are actually making use of quantum computers, in particular quantum annealers. And I actually have a live demo of the D-Wave quantum annealer I am going to run once all said and done. And the good thing is, this is one of the last talks of the day. I can run a little long, so you can stick around, and if I'm a little bit long, I'm a little bit long. So, a little bit about me. My name is Nick. I actually am working on my doctorate at UMBC down in Baltimore, Maryland. My research interests are quantum computing, computer networks, and cybersecurity. I've been working in all aspects of technology for 13, 14 some years. I've actually forgotten at this point. But the past decade or so, I've been really focused on consulting as like a network architect, doing enterprise, service provider level network design, and so forth. And I've actually spoken at Fosscon the past 2 years, and I've actually given talks over BGP and MPLS and networking concepts. So I see some guys in the back, they remember me. That's awesome. So, thank you. So, what is quantum computing? It is essentially, what it's doing is taking principles of phenomena from quantum physics and using it as an actual model for computation. Essentially, that's a very generic, high-level overview of what it's doing. We have other models of computing. This is taking quantum physics and making it a model for computing. And actually, it was actually really coined by Dr. Richard Feynman, and I believe in the late 80s or so, before he passed away. And he was really kind of pushing this, and unfortunately, he passed away. And then people have taken it up. So a lot of development has kind of started there. I can't even read my own slides. So it is vastly different, but not entirely different than classical computing, and you'll see why. One of the things that I like to say is a very, very simple high level. In your classical computer, you have a bit that's 1 and 0, but there's this concept known as superposition, where in quantum computers, it's 1 and 0 at the exact same time, and any combination of what 1 and 0 can make. So currently we have quantum computers, depending who you talk to, mostly physicists. That's debatable if they're truly quantum or not. It's more of a religious debate. But it's still very, very early. It's in its infancy. So we're kind of pioneering this field. And it's often been compared to like the punch card era in the 1950s, when hard drives took up the size of a room, there's vacuum tubes, that sort of thing. Because that's kind of where we are. We've come a long way between now and then, in the 80s and then the quantum computing era, but we're still very much in the infancy there. So IBM, there's a couple of companies, IBM, D-Wave, IonQ, 1Qubit, Rigetti, and Honeywell recently, they all have quantum annealers, which are, again, they're debatable in quotes here if they're actually quantum or not, but there's a lot of pre and post processing to actually get useful data out of it that has to be done classically. And I'll kind of explain some more of those details coming up. So one thing that's really interesting is, like before, there's not really, when it comes to the hardware, there's not like a standardized assembly language like you would see on an Intel chip or anything like that. However, when you get into the software simulators, they all have their variation of, they usually call it QSM because they're not terribly creative when it comes to naming there, but that's kind of what they all go by, more or less, which that is kind of an assembly language overlay, and they use emulated processor to kind of do that, but they just essentially they're able to encode qubits to run on that emulated processor. And I'll actually talk about one, a really good friend of mine that invented later on a little bit. So there's a lot of math in this, just like in the early days, but there's many, many disciplines of math that are kind of interchanged, so to speak, to actually make this work and explain this. Linear algebra probably being the biggest one, and if you guys were at Walt's talk earlier this morning, he actually did a remedial math for programmers, and he touched on a lot of the linear algebra concepts here. I'm not going to go into too much mathematical detail because I'm going to gloss over that because there's literally books and tomes that can be dedicated to a lot of these math, but linear algebra, geometry, there's a lot of statistics and probability theory, abstract algebra, group theory, calculus, and several other disciplines of math that I've probably never even heard of.
Partial differential equations.
Yes, that's actually calculus, yep, very much so. Which I don't know that well, but don't tell anybody. So it really does help to have a background in math as well as physics, but it's not required. So, and then, well, I should say quantum mechanics and classical mechanics, I should say to be more specific, because you talk to physics guys and that's a whole other argument, so to speak. But for simplicity's sake, we'll stay it there. So just a quick review of what classical mechanics is. That's essentially what known as Newtonian physics. So based on the laws of motion that Sir Isaac Newton came up with back, I don't even remember the date, a long time ago. You know who Isaac Newton is, I assume. And then quantum mechanics focuses on what's known as the wave-particle duality and quantization of energy. So what that boils down to in a nutshell is it a wave? Is it a particle? Is it both? Is it something else that's a combination of the two? Is it nothing? That type of thing. That's kind of where the quantum world goes into. And with that said, I'm going to talk very high level with something called Hilbert spaces that quantum computing makes very, very heavy use of. And Hilbert spaces essentially were created by a guy named David Hilbert, who was a mathematician, and it's actually known more formally as an abstract vector space of complex numbers that essentially generalizes a Euclidean space of n dimensions, where n being the number of dimensions, 2, 5, whatever. And complex numbers are essentially an extension of real numbers, which are like your floating points, for instance, to include the set of imaginary numbers. And I can't explain imaginary numbers that well, but they're just used for an extension. You go from there. So, long story short, it's a multi-dimensional container. And then vectors, we will get into vectors a little bit, that are containers within this huge, huge space. So we typically, in quantum computing, stick with spaces, or probably, which I'll talk about qubits here shortly, of 2 to the n, where n is the actual number of qubits we're working with. So you can just see how it exponentially, when you have in the thousands of qubits, which we're hoping to get to at some point, that the space is just massive. But there are something known as q-trits and q-dits, which is 3 to the n and 4 to the n. And there was actually a very recent, I think in the past 2 weeks or so, somebody did something pretty fascinating with q-trit. I can't know if it was something with quantum teleportation or not. I don't remember all the details. But it's actually a pretty fascinating little blurb. So now, let's talk about qubits. So a normal bit, historically, it's actually been referred to in this context as a Shannon bit. So if you're familiar with Claude Shannon, he essentially was the pioneer of digital electronics. And I suggest you read about him if you can. He's a real fascinating guy. And without him, we wouldn't have what we have today. We wouldn't have anything digital. And I think he's often underappreciated in a lot of ways. But so we have, which essentially that's 1 or 0, true or false. A qubit essentially is we have a superposition of 0 and 1 at the same time, where one of the numbers tells you the probability of being a 0 and one of the numbers being the probability of 1. And I have some kind of funky notation that looks like it's referencing a vector. I'll explain that in a minute here. And one thing I also wanted to point out, and I'm going to try to point out this as much as I can, in the literature with computer science and quantum physicists, they're a little bit at odds, and one being so with their indexing system. And I'll get more into that, but essentially computer scientists, we index from 0. Physicists and mathematicians index from 1. And to make things even more confusing, they see -1 and 1, and that's our equivalent of 0 and 1. And you'll see this interchangeably done in the literature, and usually if it's a quantum physics guy trying to write about quantum computing, he'll use that, then he'll switch over to it, and back and forth. It's immensely frustrating. So you saw some interesting notations here. That's actually known as the Dirac notation, or the bracket notation. And it's used to essentially represent a quantum state. And remember, essentially with the qubits make up the quantum state. And they really represent vector spaces, and this is all within the Hilbert space. And there's actually 2 pieces to the notation, the bra and the ket, and together they make bracket. You know, again, people thinking they're creative with the naming here. So a ket is actually the most commonly used, and it represents a column vector. A bra is representing a row vector. And it may seem like they're representing some of the same information, and put together they essentially are in a way. However, taken separately, they actually have different independent uses for And they can tell you different things, and it eludes me why that specifically is, and it just depends what you're doing. Sometimes it makes no difference, other times it does. So this is something I kind of added on the fly because I thought it was important to cover, at least at a very, very high level, is this concept of eigenstuff. So you have, well, like, what is this eigenstuff? So you have eigenvectors, which are vectors that are non-zero and only change by a scalar factor when a linear transformation is applied to it. That's the very mathematical, wax poetic definition. And then the scalar that actually uses it to scale the size of the vector is actually known as the eigenvalue. And these are used all the time in quantum computing because we're dealing with vector spaces. This is how we do a lot of linear transformations and so forth. And as a note on some of the notation, you'll typically see the eigenvector is by a v, and then we typically use lambda, the Greek letter lambda, to represent the eigenvalue. So if you see like lambda v, that's eigenvalue by the eigenvector. You're scaling that eigenvector by that eigenvalue, the eigenvalue, excuse me. So qubits and brackets. So we typically use kets and bras to represent qubits. However, typically kets are the most common. And if we want to do different linear transformations on it, we may change it, so to speak. But a single qubit, it's really nothing but a vector space. It's just a space that holds this information. So we can do some math on them. In particular, you may have heard of a tensor product, but it's actually a special type of tensor product called a Kronecker product that's actually done. And that essentially is what expands our quantum space. And that's how we can expand it exponentially. We take these two qubits, put a Kronecker product on it, and now say for a qubit of size 2, now we have this qubit of size 4. And also it's known as an outer product as well. And another thing about with notation is in a lot of literature, in my first example, I have a zero, not a zero, a circle with an X through it. That's the official, you can actually know as O times or the tensor symbol. But in a lot of the literature, you'll have a ket and a bra next to each other like it is on the slide, and that's usually implying a tensor or a Kronecker product in the literature itself. And so just to say that's omitted, if you ever go through the literature, like, well, why are these two things together? It's just implied. So we have what is called noise in quantum systems. And if anyone's ever done any kind of signal analysis or anything, you're probably familiar with the concept of noise. Radio noise, other things like that. But so with quantum systems, we have classical noise, which is due to classical things, like the variation of the thermal energy of the laser emitter, vibration, somebody coughed in the lab, or other reasons we don't know. Quantum noise actually is also known as decoherence. And decoherence is the loss of the state of the quantum state of information. And one interesting thing that one of my professors brought up a couple weeks ago and I thought was fascinating is that quantum physicists love studying noise. It's a phenomenon that happens. They love studying the effects of noise. Computer scientists don't care about noise. The only thing they care about noise is getting rid of it or getting back to the ground state as much as possible. And that's so they can get an accurate result. Do you have a question?
Quick question. You mentioned classical noise in terms of someone coughing in the lab.
Yes.
Is that during the collection of data, or is that coughing while the processor is, like, I guess I'm not really sure what that noise is.
It's more of a
Where is that noise introduced?
It's more just noise introduced, sound and noise, like I'm talking right now, that's vibrations, right? That can cause vibrations. That's kind of a pretty bad joke to say unknown reasons. So kind of like that. So it could be that. It may have no effect. You don't really know until you measure it and stuff. But the point is it exists in all various forms. And if you really want to get technical, quantum noise kind of exists no matter what because everything's entangled with everything else based on quantum theory. But I'm not going to go into that because that's also kind of a big religious debate depending who you talk to. So what I was speaking about with qubits before was kind of the same principles apply, but I was speaking about physical qubits on the actual silicon itself. So they're very, very noisy and they lose their quantum state really quickly. So we have this concept of logical qubits. And we have quantum error correction, which is actually a set of algorithms and other methods to essentially reduce the overall noise. And if you've ever done, again, signal analysis or anything, there's algorithms that reduce overall like radio noise and other things like that. So even with logical qubits, we still need some error correction. And another interesting piece with logical qubits is you get you could say have two physical qubits make one logical qubit, so you can get a form of redundancy. In addition, you can actually, I believe, depending on the system, share a physical qubit with one logical qubit to another logical qubit, and that's actually kind of a marketing trick. They'll use to say they have so many thousand qubits. It's because they're using the same physical qubit in more than one logical qubit. So, but the really big thing is, other than redundancy, is we have a longer decoherence time, so it hangs on to the quantum information longer. And that's exactly what we want for measurement and other purposes. So now we can talk a little bit about quantum states and quantum systems. And a formal definition of a quantum system is a portion of the whole universe taken to analyze the wave-particle duality in that system. A quantum state is a particular state of everything going on in that system at the present time. So essentially, back to the wave-particle duality, is a wave. There's this famous experiment called the double slit experiment, where you shine the light through a slit, and then when you observe it up here, it's a particle, but behind it you actually see a waveform forming. And a quantum state is essentially like a snapshot of that system. And so all the data and all the linear operations that are occurring at that time, so, and I'll get into a little bit more of that in just a second. So, one thing I wanted to point out is you'll see a lot of references to energy and amplitudes when reading about quantum computing, and that has to do, it's interesting because we're going from digital kind of almost in a way back to analog of sorts. So we're talking about like wave functions and all these other things. It's not quite analog, mind you, but it's kind of a nice reference point. And so this is all the quantum mechanics stuff coming through. And and quantum computing is kind of a very thin layer on top, so to speak. So very much like classical computing, we have registers and CPUs. Quantum CPUs can also have registers. Now it's quantum registers, but we use actual qubits and logical qubits. We can actually make registers on the fly with these. And that's essentially, in manipulating them in however way, shape, or form, that's how we can get a quantum register. And often you'll see, okay, we have so many qubits via the register. We have maybe a 10 qubit system. We can use like 5 qubits as the quantum register, and then 5 to do data and other things. But remember that everything's a vector space. So it's essentially a mathematical construct as well. So we can, when we do a lot of the mathematical operations, we essentially get a large matrix that contains the state and all information. So very much like digital circuitry and so forth, if you've ever done VHDL or Verilog, we actually have quantum logic gates. So they essentially are the quantum counterpart, and what they're used to build, essentially map out, is what's known as a universal quantum computer, which I'll explain a little bit more in the 5 types later. And they're usually represented as a unitary matrix, which is actually a special type of square matrix. So that means it has an even number of n by n dimensions. It's because you can have matrices that are like n by m, or where the numbers essentially line up. So as long as it's essentially a square. So most, I don't want to say most, but many of the gates are single qubit gates. So they operate on just one qubit at a time. However, there are gates that operate on multiple qubits at a time, and that's actually what causes quantum entanglement of the data, and that's where things get really interesting. And I'm not going to get too much into quantum entanglement because it is a whole library of information and theories about that. But here's some common quantum gates that we have. We have the Pauli gates, which kind of coincide with the rotation of an electron along the y-axis. For the y, we have the x, which is the NOT gate, and then we have like a phase flip, or there's another name for the flip, I can't remember. And then we have the Hadamard gate, which actually puts it in the superposition. Then we have swapping, then C-NOT. C-NOT actually is a 2-qubit gate. Swap is too, but I don't recall if swap does entanglement. I know C-NOT does. So this is actually just a small diagram of what a quantum circuit looks like when you're building it out and laying it out. So you have your qubits on the left there, and you have your lines on the right, and then you have H. H means Hadamard transport, and the other gates those are 2 C-NOTs. But on the right here, you're applying these to these 2 qubits, you're putting those in the superposition, you're applying C-NOT gates, you're doing other things, and then eventually you get to this thing called a measurement gate. So that's when we actually do quantum measurement to get a state of information, which actually I almost got ahead of myself, so this is actually good. We're right here. This is where we actually measure the state of the actual system, and we essentially get a matrix back. And the theory is when we measure a quantum system, the state collapses and we get a return value, so to speak, but it's essentially just a random bit of data that is absolutely useless to us. So what we're interested in is the state. And the reason being is we can actually convert that to a linear equation and then solve a system of linear equations. So when I say collapses, that's our best guess of what happens, because if you've done any quantum physics before, if you observe some quantum physical phenomena, when you measure it, actually, the way they describe it as the wave function collapses, but that's essentially their best guess. But truly, we don't really know what happens. That's kind of the beauty of quantum. You can lie about it and be right. So, not that I'm lying, but maybe, I don't know. I don't think I'm lying. I'm trying not to lie. But so to get useful results, we get the state returned, we get a system of linear equations, we solve those equations. But in addition, we actually have to do some not random sampling, but sampling over a period of time, because we eventually get a probability distribution of everything, of essentially how many times these linear equations occur. And a lot of that's all done as part of the post-processing. Not so much the sampling is done on the quantum side, but then solving the stuff is more like on the post-processing, and that's typically done classically, for now anyway. So, and usually you want to do like 1,000, 10,000 samples, and I think in my demo I'm doing like 10,000 samples or so. But to actually do the measurement, there's this other matrix called an observable, and it's very carefully crafted based on your input data to get the desired result, or a close to the desired result at a very high level of probability. Most of the stuff I've worked with is try to get like 97, 98%, but definitely in the high 90s or so, and that's where probability comes in. And essentially, classical computers are very deterministic. Quantum computers are probabilistic. If is that a word? I think. Okay, thank you. I thought it was a word, but I couldn't remember. So now we're going to talk just briefly about quantum entanglement, because this is part of the excitement here. The formal definition is you have a particle, and it has another particle, and interacts with each other. They essentially become intertwined. You no longer have the identity of either other particle. It's essentially this other new entity mass. So it's like you have 2 cups of sand, you pour it in the same, and you mix it into the same jug. You can't differentiate what sand was in one, what sand was in the other. That's essentially what's happening here. So, but with quantum computing, as I was mentioned before, we have a multi-qubit gate. We put it on 2 qubits. So if I have qubit A, qubit B, they have their own independence, their own states. I entangle them. Qubit A and qubit B don't exist anymore. All we have is this new entity that's entangled. And again, an example is the CNOT gate. I bring that up a lot because it's a very, very common gate. And CNOT actually stands for controlled knots. So essentially, just a very quick overview of the CNOT gate is that it has a control on it, and if it's triggered, it basically does a knot on the gate, on the qubit it's done to. So that's why it kind of entangles those two. And then there's this concept of oracles and black boxes, and as a computer scientist, they're extremely frustrating because quantum physicists very much enjoy, essentially what this is I have this black box thing that I put this thing in it, I get this thing out of it, I don't care what it does. And it's really frustrating when you're trying to simulate or do this type of stuff because you have to implement it yourself, and then you go back to the quantum physics, how do I implement this? I don't know. I don't know what the hell this does. I don't care what it does. I just want my output. So it's very, very frustrating talking to physicists about that because you essentially have to, like one example is I want to do like a coin flip, right? I have to write a function that does this coin flip. That's my oracle. That's my black box. The physicists don't care how it works. They just know it's going to give me this result based on this probability. But when you're building it, it's like, it's like an egg before the chicken before the egg. I don't know what I'm doing thing. And so, I covered all that. I was making sure I didn't miss anything there. So now we have a pretty good foundation, so to speak, to talk about some quantum algorithms. And they are essentially algorithms that run on a quantum computer, not too exciting there. But what they actually do, what differentiates a quantum algorithm from a classical algorithm, other than running on a quantum computer, is that they actually exploit superposition and quantum entanglement, and they can be exponentially faster than some of their classical counterparts, depending on what it is. I'm not exactly one of those people so far that thinks quantum's the solution to everything. I think quantum has its place and classical has its place. Classical I don't think is going anywhere for the foreseeable next century probably. But there is going to be things that quantum can do definitely better, but there's definitely going to be things that classical will do a lot better, especially since there's time tested over time. So, and there's kind of going back to signal analysis and DSP and such, there's this concept of the Fourier transformation, which has to do, which I can't really explain too well because I don't have that much of a background in signal processing, but a lot of the algorithms make heavy use of the quantum variant of Fourier transformation. I'm may have mispronounced that.
No, that's right, 48.
Is it 48?
48.
Okay,
48.
good.
And it's capitalized, sorry.
Oh, is it? Yo, I totally didn't capitalize that. I'm sorry. Well, hopefully he doesn't get too mad at me.
I'm not.
Oh, and I was talking about the other guy, not you, the Fourier guy. I think he's dead though. I think he's dead, so it's
Yes,
probably
he's
okay.
dead.
So-
19th century.
Oh, wow, is he that old? Wow.
Well, he's not dead.
Well, no, he's technically alive. In the quantum world, he's technically alive in some state. And he's a state through this presentation, not to get all weird and spiritual, but that's kind of, in a quantum state, he's alive.
In the multiverse, he's giving this presentation.
Exactly, in some other
He's
universe,
got
he's
beautiful
alive and dead.
plumage.
I know, right? And he's looking through the portal at me. He's like, "What the hell is this guy doing?" You know, he's lowercase in my name, not taking me for respect. So some famous quantum algorithms. There's several more, but I want to keep it brief. Deutsch-Jose, which is essentially a query of a black box. That's that's one of the foundationals to actually start quantum computing. Is just and essentially just query this black box for information. Then there's Simon's, which is also a black box query, which actually was the foundation for Shor's algorithm, which is the one that has to do with factoring numbers and will eventually probably break RSA. That's the thing. That's got a lot of this interest with encryption and quantum crypto and all that stuff. So it's not there yet, and there's a lot of work to be done there. But that's definitely where a lot of people, especially the security people, are scared, and some of the other people are licking their chops. I guess it's kind of a duality thing. Depending who you're talking, and Grover's is just like a quantum linear search. So now we have different types of quantum computers. There's actually 5, and there's probably more that I don't know about. The most common is the adiabatic quantum computer, or the annealer. And what this does is you're essentially getting a minimum global state, or to be more formal, it minimizes the Ising Hamiltonian. So, and it's really used for optimization problems, if you're familiar with NP-hard, NP completeness, that type of thing. So, like traveling salesman is, I believe it's NP complete. It might be NP hard. I can't remember the specifics now off the top of my head. I should know that, but I forgot. But anyway, it's used for things like that, just optimization, like traffic flow problems is a really common one. Then there's the analog quantum, and which is also known as a quantum simulator, but this is the hardware one, which is interesting. I don't know if any of these exist yet or if they're still in prototyping, but they are used to simulate the complex quantum interactions and be able to trace things they couldn't trace before. And this is where we're going to really start to see improvements over classical computing. And then there's this universal, as I made reference to before, which is known as the holy grail of quantum computing, where essentially you have a laptop, I'm going to put a quantum CPU in it, it's the most general purpose quantum computer. That's what everybody's striving for at some point. But we are so far away from that. We're getting there, but it's decades and decades away, I think. But who knows? You know, people have random thoughts and like, hey, this will work. And then this relatively new is actually released by D-Wave. I don't work for D-Wave. I just happen to use it as part of some university research, so I'm not promoting them over the other. But it just happens to work. Just happen to be working with that way, and I have to work with some others anyway for benchmarking. But they had press releases, but like a lot of press releases, they say all this stuff, but they say have all these words, but they don't really say anything about it. So that's kind of what happened here. And the best I could piece together is essentially it has a quantum CPU and a classical CPU in one machine. Is basically how I've gathered it. I could be very wrong, but from what I pieced together, that's like, okay, this is essentially 2 computers stuck together. And then there's this other one called measurement-based, which is, I don't think it exists yet either, but it's theoretically possible, where we have just some random entangled state, and we just keep doing a sequence of measurements until we get the results we want. And then quantum simulators, but software. These are actually things that you could run on your computer today, and essentially it simulates encoding into qubits. And the first one, I know the creator of this very well, and he's actually been a very good mentor to me as well. And it's called Crack, Q-R-A-C-K, and it is completely free and open source. It's a C++ library. It actually does a lot. It's actually based, and it also uses a quantum assembly, and it bases on the emulation of the MOS 6502 processor, but it just essentially designed to do quantum processors. And then Microsoft Q#, the language I believe is free, and the development kit is free, and a lot of it is open source. I don't think the runtime is open source, but I can't remember. And then there's IBM, I think it's Qiskit, and I think it's in the same it might be more open source than Microsoft's. I don't remember off the top of my head. but a lot of it is free and open source. So for the FOSS community, or the FLOSS community, however you choose to say it, that's actually really awesome, because it's not this super hidden proprietary stuff, so to speak. Some of it, at least, so you can get running on your own machines. And there's a lot more, and there's a lot of resources out there for this. So there's been a lot of work done today, even in the very early pioneering stages of quantum computers. Is the Russell Park Cancer Institute, they're actually using the D-Wave to optimize IMRT radiation treatments. Booz Allen Hamilton is using it to optimize satellite convergence. Volkswagen is using D-Wave for they've actually done a lot of really good experiments with real-world traffic flow optimization. And then there's this company called Accenture is actually utilizing a company called 1Qubit, which is also an annealer. They're doing molecule comparisons to accelerate drug discovery for neurological and neurodegenerative research and conditions. So now, talk a little bit about the demo I'm going to do, and hopefully it doesn't break on me, but I've been testing it a lot, so it should be pretty good. So you can actually get on D-Wave for free. They have a cloud platform called Leap, and you can sign up for free and get an API token. I think the only biggest thing is your limit on how much time you can actually spend per month or per day. I don't know the metrics. I'm with the university, so we're doing research, so we get more than the free account per se. But as far as I know, I don't know what the limit is. But usually, most of the stuff you're going to be doing is it'll be maybe in the milliseconds when it comes back. The actual quantum, the transport of the data is going to take the longest. The quantum data stuff is really quick for most things, but I haven't done anything too significant. So they have a C API and a Python 2 API. I don't think it has Python 3 support yet. And they actually have a lot of really good documentation once you sign up for Leap, and it's actually available as Jupyter notebooks. So if you guys have used Jupyter notebooks before or heard of that, then it's actually really, really nice because you can actually see it on their site, and it actually gives you some of the code stuff. So this is what a part of the quantum CPU on the D-Wave 2000Q looks like. So this is a unit, that is just one unit cell, and these actually what is known as a chimera graph. And this is how each one of those little circles is a qubit. This is how they're all wired together. So, and that's just like a small subsection of that. So it's really, really complicated wiring diagram. So there's actually, and I'll talk a little bit about, I'm just going to show the way to manually embed and get results, because I think, excuse me, I ran out of talking fluid. So there's heuristic embedding and manual embedding. Heuristic embedding is basically you let the quantum computer decide where it's going to map and embed your problem. Manual embedding, you can pick what qubits you want. And usually it's preferred to use the heuristic embedding because some qubits can be bad depending on the system. But I'm just going to show how to do it manually because I think it gives a better idea of how it actually works. I'm one of those people that I have to do it several times over before I understand even a little bit how it works. So you have to formulate your problem to fit on the D-Wave. You have to formulate your Hamiltonian. You have to you have to essentially encode it into a graph for the D-Wave. Choose your result type as well as the amount of sampling. Then you submit it to the solver. Then you'll get some raw results back. You have to decode the results, and then you hopefully print the results. Unless you don't want to see them, then that's your business. But so yeah, there's a lot of steps. You can see how it's very early on to like vacuum tubes and punch cards and other things. Yes.
Hamiltonian is capitalized. Hamiltonian is capitalized.
Man, you're just beating me up today.
Well, I assume if you're going to be using this PowerPoint again,
yeah, I probably will. That's actually, I know, in all seriousness, I greatly appreciate it.
I'm sure you do.
I do. I'm just trying to give you a hard time.
That's okay.
I'm giving you a hard time because you're giving me a hard time.
Please don't look at it that way.
No.
We're in this together.
I know, I hear you. So,
what does that even mean, your Hamiltonian?
That is a very good question. I'm not sure how to explain it correctly, to be honest.
I think 99% of the people here have that question.
Essentially, a Hamiltonian is known as a Hermitian operator.
Oh.
If that helps.
That's it.
If that helps, it's a Hermitian operator, but really it's essentially a...
It's that partial differential equation, Hamilton's equation, that describes a quantum mechanical system.
Thank you. That's way better than I could have explained.
It's an optimization thing.
Yes.
Instead of optimizing a value, optimizing a function.
Yes. Thank you. Well, maybe you guys should be doing it, not me.
No, you're doing great.
Yes, fantastic.
So there is a few to be fair, the Jupyter the documentation, it's fantastic, and they read the docs platform or whatever that a lot of open source projects use. It's really good. However, some of the problems I thought were kind of difficult for me, just because the way I read through things and understand things. I wanted to kind of make my own version of a problem. So we essentially have, here's our problem statement. We have a 3-node graph. I want to embed it on a 2000 queue, and I want to assume all the nodes are going to start out as a superposition of red and blue. And I hope those are purple, because I'm actually colorblind. But I hope those look purple.
Yes, they are.
Okay, thank you. But so what I want to do is come up with only one solution where the one node is red and the rest are blue. So that gives us what? 3 possible solutions. One node based on just these 3 nodes. And obviously that would expand more if you have a lot more nodes. So some more details is, I mentioned before, this Ising Hamiltonian, and I didn't use the LaTeX very well, so I apologize for that. And that's just kind of the map that kind of what the Hamiltonian is. But for simplicity's sake, the value 1 is going to be red. It's going to represent red. The value -1 is going to represent blue. And then now we need to actually map the problem. The D-Wave supports, like I was saying, it supports manually mapping the problem directly to qubits, or to utilize their heuristic libraries to deal with this. And that's great, and that's the way I would suggest to do it, but I kind of, for explanation's sake and educational sake, I thought it was better to do it manually. So we have node 0 going to qubit 0, node 1 going to qubit 4, node 2 going to qubit 5. And that's just some of the code, and I actually will have the code posted with the slides towards at the end. It might even be up there, but now I have to correct it a bit thanks to Mr. Hamiltonian, which is fine. That's actually really good. I need to be corrected. So, and those are just some of the raw results. Now I am going to bring this over. Oh, I have to get on my presentation. That's probably okay. No, don't spoil it. There. Okay. Can everybody see that okay? Or do I make it bigger? A little bigger? Let's see what I can do with that.
I can see it fine.
Like a zoom view.
Oh, I can do that? Oh, I can do that.
That's right next.
Okay, cool. So I've actually got this already written. So let's see. Okay, I don't remember where I put it. I thought it was here. There we go. Oh no. What is supposed to happen? Oh, maybe it's the internet. That's why. I thought it was working. Oh, what the heck?
Did you set up your computer to work on the Wi-Fi?
Here, let's try to connect it. Okay, cool. That's what I wanted. Eddie Rome's here, and Eddie Rome is like the education thing.
Oh.
Why is it not? Unless I'm just not getting signal.
Edero?
Oh, I don't think we have
Eddie
Eddie
to
Rome.
log into?
For Eddie Rome? Yeah, I have it saved though.
You don't have Eddie Rome here. I've tried it.
It worked for me, I thought. So,
I have Edge Room right now.
yeah, so do I on my phone, so I don't know why it's doing
Oh, on your phone, it's different, yeah. If you use your
Are
phone.
you connected to the Wi-Fi?
Yeah, it should be. Trying to do things. Hold on.
I have the password for the Wi-Fi if you need it.
There, I don't know what that was about.
You got it.
Networks. Networks will be networks.
Just making sure. Okay, slight technical difficulties.
Now, where is this running? Is this running on your laptop?
Yes. I hope it's running.
Okay.
So what does a D-Wave
Where's the
2000
D-Wave?
physically look like?
Oh, good, it did run. Good deal. So now I'm going to do all this explanations. So first I'll show you, there's pictures online that show it. It's pretty impressive, and the quantum CPU and stuff. I guess I should have included pictures of those. That would have been really smart, huh? Oh well. So this is all the results we get back for just my simple little problem. So this is the timing information, and these are the number of occurrences. These are the energies. And then we have all these random interesting data here, that a bunch of threes, and I'm going to explain that here in just a minute. So let me go back here. Did I do that before? I don't know. Full screen. Present. There we go. Present. There we go. I don't even know how to use a computer. Anyway, so this is a sample I did before, and that was a different sample. But so here's essentially the raw data we have, as you saw. So now we have all this raw data. What does it actually mean? It looks like a bunch of freaking threes and ones, and I have no idea what I'm looking at. So the good thing is we're only essentially, the way, and I didn't include this and I apologize for that, but essentially as far as, and there's no whiteboard in here, I don't want to draw on the wall, but essentially in the actual graph of the quantum CPU, qubit 0 has a link to qubit 4, qubit 0 has a link to qubit 5, but qubit 4 and qubit 5 have no direct connection to each other. So it looks almost identical to my graph that I kind of say. So we essentially have to reverse our mapping. So I'm sorry, before I get to that, because of that, the way you submit it, and you'll see this, I commented on the code, is that we're essentially using the first 6 qubits. So we can actually just take a small sample of those qubits here of what we're using. So I've got a few more to show context here, and we have 1, -1, -1, 3, and 3. So now we just need to, okay, qubit 0 is node 0, qubit 4 is node 1, qubit 5 is node 2. And then we have our decoded results right there, and there I actually, before I fixed the printing, but node 0 is 1, node 1 is -1, and node 2 is -2. I actually have a little bit better of a version here. And if we go down, there, I actually have a function in Python to actually decode it for me, doing just some dictionary mapping for me, just to, and you can see node 0, 1, 2, just to make my life easier. And it looked cool, and it made me feel like I accomplished something, so I'm good for that. So our final results, we have the value 3 basically refers to any qubit that is unmeasured or is just not used. So we apply the reversal mapping, we have this little chart where node 0 is red and then the value is 1, node 1 is blue, -1, and node 2 is blue and also -1, so we actually have our solution. But one thing I wanted to point out with the raw results that's interesting, I almost didn't do this because I thought, because there's things you can do on the qubits to actually have biases, so you only get a few, you can essentially tweak it and get only the solution you're looking for. However, this actually shows we have number of occurrences 9992, 4, and 4. That essentially means out of 10,000 times we ran on the quantum computer, 9,992 we got the first solution, 4 times we got the other solution, and then 4 times we got the third solution. So that kind of helps illustrate, it's really just probability. So it's fair to say that 99% of the time we got the first solution, the other times it's like less than 1% we got the other 2 solutions. So back, and yeah, now we have some questions. Hopefully I can answer them. So, yes?
What are are there any limitations to using a simulation rather than an actual quantum computer?
Yes, there is, because you got to remember you're still running it on classical hardware, so you're not going to be able to get the full benefit, obviously. However, there are things that are done with essentially that's where a lot of probability theory comes in, and it basically analyzes the wave amplitude and the energies, and it gives you a probability of how this is going to happen. So that's how we can actually encode qubits. So it doesn't really have like with the quantum computer, it has every single value possible. That's part of the superposition, it just has everything. You obviously can't do that, and you'll get like a, not memory out of bounds, but a stack error, for instance, or something, right? You run out of memory. So essentially, that's where like the probability distribution comes in, and essentially there's other methods as well you can run on that to kind of get the most likely, and that's tied into the algorithm, the probability algorithms and such you're looking for. So,
My guess would be that you're taking 10,000 tries, which would be one real quantum.
right, exactly. So essentially you do it on the physical quantum computer, you have 10,000 tries, but they're all happening at the same time. They're not necessarily happening at the same time on a classical computer because they can't, because they're just physically not capable. But there's probability and stuff of what's likely to happen, and that's kind of what it picks from. So that's how you can kind of encode it. It's actually relatively simple to encode qubits with classical hardware. That's why there's a lot of simulators and other things.
You mentioned your website, and it was accessible. Can you give us your URL or?
Oh, which website? It's
Yours.
on my GitHub. Like, you mean for the slides and the code?
Yeah.
Oh yeah, that's on my GitHub. I don't know if I think I have it in the references, but I could definitely give that out. I didn't even think about it.
If you're willing to, I'm sorry.
Oh yeah, absolutely. I want you guys. I mean, I don't know about. I'll give to everyone else but you. How about that?
Okay.
Because you'll get me on my capitalization again.
That's what I'll do. I'll prove it for you.
There you go. No, then you'll
Okay.
write a proof and say how everything's wrong. I'm like, okay, now I have to redo everything.
You got Hamiltonian correct when you used it later, so.
Oh, good. That's actually really good to hear because that was one or two of the things I was worried about getting wrong. I'm like, oh man, I hope I understand this well enough to explain it. But so let's see. Any other question? Oh yes.
This is sort of like if you would confirm my understanding, but the point of having qubits or quantum simulations on classical hardware is to provide a sort of API that we can use to develop software that's ready to go when quantum hardware is really available?
You could say that. It's more to do some experimentation on some. Essentially, it boils down to you're trying to implement some like a universal type of quantum computer. So you're trying to implement gates in software, basically. So it's essentially trying to model out and map with a certain of what we would expect to get before. So yeah, you can use it as kind of like a precursor to doing things like that. But sometimes it wasn't available, so it's just a way to do that. So you could use that for a lot of different ways, and sometimes it's more difficult to actually have access to a quantum computer and that type of thing. It's getting more available now, but that's only been in the past year or so with IBM pushing their IBM Q system and stuff. So, but you can still do a lot of work with just the simulators and prove. And you can even, if you're familiar with like Maple, Sage, or Mathematica, you can actually write a quantum simulator doing that just using any computer algebra system. So, because it's really just all vector stuff, matrix multiplication, essentially. It's more complicated than that, but simply put. Yes?
The annealer that you were talking about, is that a simulator or an actual simple quantum?
That depends who you ask.
Okay.
That is one of the religious debates, depending who you ask. I will say there are some things that it has, the results have, in other experiments I've viewed and witnessed, it has demonstrated quantum mechanical behavior, but a lot of the mathematical theorists for quantum physics would completely disagree. So if you're talking to a computer scientist, a pragmatist, or a complete mathematical theorist, you're going to get a different answer, and you're going to get a religious debate. So I would say at this point, yes. But what's actually really cool, I actually should have talked more about this, but down in College Park, Maryland, there's this company called IonQ. They're actually doing an annealer, but it's using what's called an ion trap. So they essentially have lasers that act as like a bus, and then they actually have trapped some type of element, some type of isotope ion, and they're actually using that to stimulate the ions, and they get the quantum information that way. It's still an annealer, but it's really cool because it's like, it has a very wide bus that's a laser, then they have a bunch of optics that point up, and they agitate the ions. I've not seen that one in person yet. I want to, so I'm hoping to work with those guys at some point. But yes.
Has anybody had any success factoring large numbers using these quantum simulations?
I don't know. I think they have to a point. I don't think it's nearly enough to break RSA or anything too interesting, but I think it's just more for how far can we get.
Yeah, I didn't expect them to actually be
right.
like a regular.
I think it absolutely can. I think I know.
Even done it,
on the annealers, it's typically kind of Ising kind of. If you're familiar with SAT or SAT problems, which is basically Boolean equations or Boolean satisfiability, and the Ising actually maps to that, and that's essentially what the D-wave and the annealers do. Is they map the Ising to the satisfy the Boolean equation. So it's essentially doing a lot of Boolean equations there. So I think there has been a lot of work to do extraneous mathematical stuff like, and I'll actually get to that Oh, where'd it go? Oh, no. And then, actually, part of my special thanks, he's actually a PhD candidate, Mr. Akinki Borle. He actually helped me a lot. He's actually doing something with, are you familiar with the least squares problem? The math least squares problem? He's trying, that's going to be his thesis, or his dissertation. He's going to try to implement the least squares on D-Wave. So, and that's actually a pretty complicated problem. Well, depending who you talk to, it can be a pretty complicated problem. It's just a matter of formulating it to a system of Boolean equations and all this other stuff. And it's funny because I say Boolean, but we're talking about linear equations, but this is just kind of talking at the hardware level. So, that answer your question, I hope? If not, I'm sorry. But
I just wanted to know if they were trying out the algorithm.
oh, they absolutely are. Oh, there's no question they are. Just how successful they are, they're debatable, and depending who you talk to. And the three-letter agencies that are typically trying those out don't really advertise their results either. So that's part of it too.
The fact that you're quantum simulating would counterbalance the advantage that the algorithm would give you on a real quantum computer.
Right.
So you're not going to crack RSA on a simulated quantum computer.
Typically, no, just because you're going to run out of space very quickly. That's kind of to your point with the hardware you were saying before. Just and Dr. Feynman actually has a very good quote about when we talk about Hilbert spaces, and the problem with Hilbert spaces, they're just so damn big. And that's literally what he said. They're just huge. And yes.
So once we get to the point where it is developed enough, where let's say RSA could be easily cracked, the danger that poses to the world, like basically whoever develops it first can sort of destroy everyone else in terms of the power. Wouldn't that mean that there's probably a lot of research going on about this that nobody would know about?
Absolutely. There is absolutely no question about that.
So it could be much closer than
it absolutely could.
Than decades or 100 years out.
The quantum state of that information is indeterminate. Let's just say that. I mean, that actually ties very well in. You're absolutely right. This is what we know about. Let's just say that. And I don't know anything else that's going on outside university stuff, and I'm not under any NDAs or anything yet about any of that stuff. But really, I'm not. But I mean, yeah, I have no clue what people are working on. You never know. They get a couple of nerdy scientists in a basement, and they give them a bunch of pizza and beer and stuff, and they just kind of go to town working on this quantum stuff. And, okay, you had one, then you had one. I'll go to you. Yes.
A decade or two ago, there was a big.
Could you speak up a little, please?
A decade or two ago, there was a big intellectual development of something called neural nets and
yes.
neural computing and so on. I haven't heard too much in the last 5 years or so about that. Compare this with that. Is one more advanced than the other in its progression towards using in something?
Well, that's kind of like an apples and oranges comparison here. And neural nets are very much alive, and they're very active in research with AI and machine learning and such. So neural nets essentially are getting a network of elements, something learned enough that essentially it can act in an autonomous fashion to accomplish things. Quantum computing is more, I'd say machine learning, AI, and quantum computing, they all kind of go hand in hand. They complement each other. So you'll get a lot more better results out of your AI models, your neural nets and stuff to run, and there's actually been running neural nets on the D-Wave. That's actually some other stuff like one of my professors was working on. He got he got a Boson machine or something working on. I can't remember all the details, but so essentially the quantum stuff is what that would actually technically run on and get exponentially faster and arguably more intelligent. That's where the AI models and stuff come from.
So together they'll actually do a step better.
Absolutely, that's kind of the goal. So it's kind of like that's how they're related. They're not the same thing though. And then was it you that had it?
Yeah.
Okay.
So there's a lot of talk about quantum computers undermining existing cryptography, but I'm curious to know if there are properties of quantum computing that could be used to develop stronger encryption.
Absolutely. That's actually, you have the people trying to break what's currently with that, but you also have, there's quantum cryptography, which essentially, in a nutshell, what's really interesting about quantum cryptography is that you use quantum channels to send your data through, and you do it with a series of quantum states, and there's different protocols that have been developed to do some of this. Some of them are early on. But essentially, you could tell if some data has been compromised because when you measure something, it'll, I believe it'll, I don't know if it'll blow. It changes the state when you measure something. That's how, like, kind of goes back to the quantum physics stuff where it's like the wave-particle duality. When you, it's a photon, it's a particle, but when you measure it, it's a wave. It kind of relates to that. So I could send you a message, somebody intercepts it, I know it's been intercepted because the state's changed.
Right.
But if you don't look at it, it doesn't change. Well, it could change, we don't know for sure. But we know definitely measuring changes it. Or so we think we know anyway.
One thing a quantum computer could give you is a quote-unquote genuine random number, not a pseudo-random number.
There is that also, yeah.
And that would be a powerful encryption tool.
Right.
Can you put up the slide with the links?
Yeah. Real quick, I just wanted to give a special thanks to Jinky Borley, one of my professors, Dr. Sam Lamonaco. He's very, very one of the people that thinks that E-wave isn't quantum because he's very, I mean, he got his PhD in mathematics in 1964 at Princeton. So he's been around a long time. He's a really good guy, though. And then the founder and lead developer of Crack, Mr. Dan Storano, and then another Crack developer and contributor who's also a friend of mine, Mr. Ben Bale. And then, thank you. Oh, yeah, I did. Okay, I was smart enough to put my GitHub link on there, too. So there you go. I have a bunch of references, and I was hoping I didn't bury it in that, too. But there's my email. Feel free to email me about stuff. If you loved it, hated it, want to talk more about stuff, I'm always interested to discuss things, debate things, understand things, get certain words and names corrected and capitalized properly, and all these things. So, and then yeah, that I actually was smart enough to upload the slides and the code last night, but I'll probably be, so what's currently I've done is up there now. I'll probably be making some changes up to it probably tonight or tomorrow, and then I'll actually upload it to the corrected version, but it's not going to be a whole lot different than, it's just going to have proper capitalization.
Is that OD or is it 00D? It looks like
00D.
Okay. Good I asked.
And all good was taken, so I had to be creative.
Thank you.
Oh, yeah. I thought a few other people had some questions. Yes?
I have a question. So, how hard is it to, I just signed it, and I signed up for the Leap thing.
Mm-hmm.
So, how easy is it to run your code there?
I mean, my code should be pretty complete, so it has all the imports and all the stuff. The only thing it doesn't have is I have a function to actually import my API token because I didn't want to put that on GitHub. So, I mean, and that's just like, you'll see it just reads a text file for my API token. That's just for simplicity. So it should be pretty, it should just work. Just remember, it's Python 2 though. Python 3 is not supported.
Yeah, I want to ask you one thing. They said to install a module. The default bit which is compute didn't work, but the bit 3 worked. So it's kind of a puzzle.
That is interesting. Oh yeah, they do have it. I forgot. I actually did it I installed it manually from their SDK.
So I saw the D-Wave Ocean.
Yeah, that Ocean SDK.
Only the tree is the one that works. So that's kind of strange.
That is interesting.
I know where you idle on free nodes, so...
Yeah, well, you guys know me real well now. You had a question? I'm sorry. I thought you had your hand up. Yes. Oh, well, never mind.
Just to clarify, you were connecting into one of the actual...
Absolutely. One of the quantum computers, depending on who you talk to, yes.
And can anyone...
There is a platform called Leap. It's free to sign up for E-Wave. I don't know how much time they limit you on it, but yes, it's free.
It's 1 minute. I checked.
It's just 1 minute? Yeah, see, we have way more because we're a research university, so, but I think it's like 1 minute, but typically your stuff should run in like 2 milliseconds.
So this stuff will take like...
It should, absolutely.
2 milliseconds.
It should take like 1 millisecond.
Well, yours probably took a while because maybe you were in a queue or something.
Well, no, what takes a while is the internet. It's all the transport. So sending the data to the cloud, to the API, once it's on the quantum computer, it only counts the time it processes on the quantum computer. And then sends it back. And then your time, that's all the compute time. The other stuff is all transport stuff.
So I just wanted to say you did an incredible job packing, physics, math, and theory of computation into such a short presentation.
Thank you. That's actually my goal because you essentially study them independently.
Yeah.
And it's a huge pain in the ass because they could never agree on anything.
And this is like I didn't really learn anything because I didn't understand much of it, but I learned what I have to learn to understand this.
Yeah,
right? So I
that's
can
kind of
go
my
in,
goal.
I can research all these things and learn
Yeah.
more about that, right?
I mean, it's still very math heavy. It's still very early in its infancy, so Unfortunately, you can't avoid it, and it's good to know how it works, but
Yeah.
eventually we'll get past that hurdle.
Yeah.
So, yes?
Any other correction? If you're correcting the spelling of Hamiltonian, you might want to put in the word operator afterward.
Yes, thank you.
Because there's two definitions of
That is very true, because it is a
Right.
Hermitian operator.
Right.
I completely forgot about that, thank you.
Hamiltonian's also a four-dimensional complex variable, and since you were talking about dealing with complex variables, it wasn't always clear which of the two you meant.